Hello friends, in this video I'd like to solve the following problem from Concrete Mathematics textbook, problem 48 from chapter 4. Generalize Wilson's theorem by ascertaining the value of the following expression, product over all integers from 1 to m, which are co-prime to m, modulo m. It is to be understood that we are first taking product and then we are reducing it modulo m, where m is a positive integer. So my hints, it's an interesting problem, first proven by the great mathematician Carl Friedrich Gauss in his great book 𝑠𝑐𝑜𝑛𝑐𝑒 𝑘. And I wish to prove maybe a simplified proof. So two pieces of handy notation. First, I like to write m perpendicular m to denote that two numbers are co-prime. The authors of Concrete Mathematics introduced this notation, and I think that it is wonderful. And moreover, I use the following Iverson bracket, which is defined as follows. Iverson bracket of some formula is 0 if this formula is false, and it's 1 if this formula is true. It simplifies notation a great deal. And moreover, notice a well-known fact from algebra, Zm star, which is defined as the set of all integers from 1 to m, which are co-prime to m. This set is a multiplicative group for every integer, positive integer m, and that means that for every k from this group, there is exactly one L, such that k times L is congruent to 1 modulo m. I will not prove it, it's a well-known fact. What I will prove is the following lemma, which is the central point of my reasoning. Lemma. Let m be a positive integer, and let omega of m be the number of prime divisors of m. Then our congruence, this congruence, x squared congruent to 1 modulo m, has exactly 2 to the power omega of m plus Iversonian bracket 8 divides m plus Iversonian bracket 4 divides m minus Iversonian bracket 2 divides m. These many solutions in the interval from 1 to m. So how to understand it? Well, for example, this part, it's either 0 or 1. If m is even, it's 1. If m is odd, not divisible by 2, it's 0. Handy notation. And also, we know that the following theorem is true. The Chinese remainder theorem states that if you are given numbers from m1, m2, and so on, ms, if they are co-prime, pairwise co-prime, positive integers, then this system of equations, of congruences, x is congruent to a1 modulo m1 and so on, has exactly one solution x in the interval from 1 to m, where m is product of these numbers. So if you wish to try it, give this problem a try, and I will see you in a minute. Okay, so my solution. First of all, I wish to prove my lemma. And I will do it case by case by considering more and more general forms of m. So first, start with m equals 1. If m equals 1, what happens? Well, x squared congruent to 1 modulo 1 has only one solution in the interval from 1 to 1. This happens if and only if x equals 1. That's because we are dealing with interval from 1 to m. One solution. What happens if m equals 2? Well, the very same thing. That means that x also equals 1. Because 2 squared is 4, 4 is not congruent to 1. What happens if m equals 4? If m equals 4, it's pretty easy to verify that both 1 and 3 satisfy our congruence. 1 and 3. 2 of course not, because it's even. 4 of course also not. And now let's consider power of 2 to the power of alpha, where alpha is greater than or equal 3. What happens now? Well, let's take a look. Our congruence, which states that x squared is congruent to 1 modulo 2 to the power of alpha, is really equivalent to saying that x minus 1 times x plus 1 is congruent to 0 modulo 2 to the power of alpha. And that of course means that 2 to the power of alpha divides our product. Okay. When does it happen? Well, notice the following. X minus 1 and x plus 1 are of the same parity. They are either both odd or either both even. They are of the same parity, and moreover, they cannot be divisible by 4. Cannot be both divisible by 4. Why is that? Well, that is because they are two units apart. No two numbers which are 2 units apart are both divisible by 4. Okay, so when does it happen? When does this congruence hold? Well, it holds if and only if either 2 to the power alpha minus 1 divides x minus 1, or when 2 to the power alpha minus 1 divides x plus 1. Why is that? Well, if this divisibility holds, then x plus 1 is even, it's even, and then this holds. Other way around, if this holds as well. Okay. And very similar with the second congruence. How many solutions do we have? Well, it's pretty easy to see that the first divisibility holds. We are talking about interval from 1 to 2 to the power of alpha. That holds either when x equals 1 or when x equals 2 to the power alpha minus 1 plus 1. Because next number, which is divisible by 2 to the power alpha minus 1, next number will be this number, and this number is outside our interval. And what about the second condition? Well, it happens if and only if either x equals 2 to the power alpha minus 1 minus 1, that's one possibility, or when x equals 2 to the power of alpha minus 1. Again, you can easily convince yourself that if you subtract or add 2 to the power alpha minus 1, you go outside of our interval. So we have in total 4 solutions. So in general, when m equals 2 to the power of alpha, the congruence x squared is congruent to 1 modulo m has exactly how many solutions? Well, either 1 or 2 or 4. And that can be written compactly in this way. 2 to the power 8 divides m plus 4 divides m. Let's convince ourselves. If m equals 1, we have 0 plus 0. 2 to the power of 0 is 1. If m equals 2, 0 plus 0, also one solution. If m equals 4, this is 0, this is 1. So we have 2 to the first power, 2 solutions. If m is 8 or above, 1 and 1, 2 to the second power is 4. Everything checks out. Very well. So let's remember that. Let's remember that. Maybe I will mark it asterisk. Next case, which I wish to consider, is when m is a power of some odd prime, where p is a prime, odd, and beta is a positive integer. What happens now? Let's take a look at our congruence once again. X squared congruent to 1 modulo p to the power of beta, which again is equivalent to saying that p to the power of beta divides x minus 1, x divides 1. And now let's take a look. P can divide only one of these parentheses because these numbers are 2 units apart. No two numbers which are 2 units apart can be both divisible by the same odd prime. So that holds either when p to the power of beta divides first number or when it divides second number. And how many solutions are there? Well, only one in each case. In this case, x must be equal to 1, and in the second case, x must be p to the power of beta minus 1. So we have only two solutions. Two solutions. And let's mark it double asterisk. Very well. And now general case. General case. Let's say that m equals 2 to the power of alpha, p1 to the power beta 1, p2 to the power beta 2, ps to the power beta s, where alpha is a natural number from 0, beta 1, beta 2, and so on, beta s are positive integers, p1, p2, ps are odd primes, and finally, number of these primes is a natural number as well. This may be, in fact, an empty product. Okay, and now let's see the following. Saying that x squared is congruent to 1 modulo m is really equivalent to saying that x squared is congruent to 1 modulo 2 to the power of alpha, x squared is congruent to 1 modulo p1 beta 1, and so on and so on. X squared congruent to 1 modulo ps to the power beta s. And now remember that each of these congruences have two solutions in their respective intervals. Two solutions, apart from the first, which has how many? 2 to this power. Okay, and now let's see. How many solutions are there in total? Well, if I can, to be honest, choose every possibility. So x is congruent to something in these many ways. Here, x can be congruent to one of these two numbers, and so on. And by the Chinese remainder theorem, every choosing of mine will give me exactly one solution in my interval from 1 to product of these numbers to m. So how many solutions are there in total? Well, product of 2 to this power times 2 times 2 and so on. The total number of solutions is 2 to the power 8 divides m plus 4 divides m times 2. How many times? Well, we have s odd prime divisors. And we can express this in other way, but I need a new page. Perfect. i.e., I can write it in the following way. S plus 2 divides m plus 8 divides m plus 4 divides m minus 2 divides m. And if you think about it, this part right here is really the number of odd divisors, of odd prime divisors of m. Because we have it's the number of prime divisors. Because we have exactly s odd divisors, prime divisors, and they may or may not be divisor of 2. So that part is exactly omega of m. So i.e., once again, 2 to the power omega of m plus m divides 8 divides m plus 4 divides m minus 2 divides m. And that closes the proof of my lemma. I need this lemma only to show the following. I needed to show only the following, that in particular, maybe write it in yellow, in particular, let's take a look. When doesn't 4 divide this number? Well, it doesn't divide it when we have in the exponent 0 or 1. And it's pretty easy to see that that happens if and only if our number is one of the following forms. Namely, either m is 1, or 2, because for 2 we have omega of m is 1 and we are subtracting 1, so we have 2 to the power of 0. 4, because for 4 we have 1 plus 1 minus 1, and it's 2 to the first power. And also in the following cases, p to the power of beta and 2 times p to the power of beta, where p is odd prime number and beta is a positive integer. Okay, in these cases, this number is not divisible by 4. In every other case, our number is divisible by 4. Very well. I will use it. So I will mark it. You know what? I will mark it triple asterisk. It will be very useful later. Okay, and let's go. Finally, let's get to our main problem. So we wish to evaluate again. Remember that we wish to evaluate product from 1 to m over numbers which are co-prime to m. of k. First of all, two situations can happen. Either k squared is congruent to 1 or it's not. So we have two products. First product over numbers which are congruent to 1 modulo m, and we have second product over all the rest. Okay. The second product, let's consider it first. The second product is really just congruent to 1 modulo m. Why is that? Well, every number has its inverse, modulo m. Okay. Moreover, its inverse is not k itself, it's some other number in this product. So we get pairs of numbers whose product is congruent to 1 because they are inverses of each other. So we are pairing numbers with their inverses. So if we pair a number with its inverse, we get 1. So we have just a bunch of 1s in this product. So our product really boils down to evaluating the first product. Okay, and now I will maybe consider a few cases first. So it's pretty easy to check cases where m is 1, 2, or 4. Well, if m equals 1, this product well, which numbers are congruent to 1? Only one. So it's congruent to 1 modulo m. The same happens when m is congruent to 2. Congruent to 2. And if m equals 4, maybe let's write it. As well. Which numbers are congruent to 1, whose square is congruent to 1? Well, it's 1 and 3, and 1 and 3 is congruent to -1 modulo 4. Okay, so these cases are already considered. I need a new page again. And now I wish to consider m which is not 1, 2, or 4. And now consider the following. I need one more observation. Let's consider, so maybe you know what I will call S. S is the set of all integers which are between 1 and m, and which are whose square is congruent to 1 modulo m. And I wish to consider the following mapping, which takes some number k and maps it to m minus k. Okay, I will call this, you know what, f. Very well. Well, this function is properly defined because f is properly defined because if k squared is congruent to 1 modulo m, then m minus k squared is congruent to m squared minus 2mk plus k squared. This is congruent to 0, this as well, and this is congruent to 1. So it's also congruent to 1. So the values are, in fact, in our set S. Okay. And notice the following, that now we can group our terms of our product, our numbers in our product, in pairs. I can map every k to this number, and what do I get when I multiply two such numbers? Well, k times m minus k, it's congruent to mk minus k squared. This is congruent to 0, this is congruent to 1. So it's congruent to minus 1 modulo m. So that means, maybe let's write it in yellow, that my product, which goes from k equals really over k in my set S, k, it's really congruent to minus 1 to what power? To the power cardinality of S over 2. Cardinality of S over 2. Yes, because exactly half of these numbers, because I am pairing this number to this number. So I cut the number of my numbers in half. And let's notice that that is what exactly? That is congruent either to 1 if 4 divides the cardinality of my set, and minus 1 if 4 does not divide it. Well, I should also say that S has an even number of elements. That should be pretty obvious, because it has one element only in cases where m equals 1 and 2, and these cases were already considered. In every other case, S has an even number of elements. 3, 4, 5, yes, and so on. And that should ring a bell for divide something. And remember, we have established, it was condition marked triple asterisk. Triple asterisk, 4 doesn't divide, because if you think about it, this is just the cardinality of our set S. So 4 does not divide the cardinality of S only in the following cases, either for 4, p to the power of beta, 2 to the power 2 times p to the power of beta. Cases where m was 1 or 2 were already considered separately. And that means that our product, i.e. our product, is congruent to 1, to either minus 1 or 1. It's congruent to 1 if, or maybe let's first write, it's congruent to minus 1 if m is 4 p to the power of beta or 2 times p to the power of beta, only in these cases, and it's congruent to 1 otherwise, where p is an odd prime and beta is a positive integer. It's a positive integer. And that really is our result. We can write our final answer. So our product from 1 to m of all the numbers over all the numbers which are congruent to m, modulo m is either -1 if m is 4 p to the power of beta, or 2 times p to the power of beta, or 1 otherwise. Where again p is an odd prime and beta is positive integer whatsoever. And that closes our reasoning. This is our result. This is what we wanted. This is what Gauss has proved in his great work many years ago. Can I fit this ellipsis? Thank you. Almost. Whatever. In particular, before you go, one more thing. One very special case. In particular, if our number is just p, then, or maybe you know what, because usually modulo m is usually defined to be a positive number, so I can just as well write m minus 1, and now it's necessarily positive. In particular, if m equals p, where p is a prime, then what happens? Then our formula says that numbers which are congruent, which are co-prime to p, that is 1 times 2 times 3 times p minus 1, it's congruent to -1 modulo p. In other words, p minus 1 factorial is congruent to -1 modulo p. That works for odd primes, but also for 2, because if p equals 2, then, well, 1 is congruent to -1. And what is it? It's Wilson's theorem. So, in fact, our theorem, Gauss's theorem, I'm not the author of this theorem, unfortunately. So, this theorem, which we have just proven, is just a generalization, vast generalization of Wilson's theorem. Or putting it the other way around, Wilson's theorem is a special case of this more general theorem. And that's it. So, thank you for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.